All right. Welcome, everybody. We're happy to have Karthik Ors here today with us to talk about his experience as an undergraduate and his experience currently as a graduate student. Just a short bio about Karthik. He is a backpacking and cooking enthusiast, and he is a current master's student in robotics at the University of Michigan. He completed his BSc in mechanical engineering and computer engineering last year. And in undergrad, he focused on building robots for extreme environments, including space. And he now conducts research on legged robots for Dr. Talia Moore. So welcome, Karthik. Thanks for being here today.
Of course, thank you for the intro. So I guess Sarah covered this, but so yeah, just a little bit about me in addition to what Sarah said. Yeah, I was born in India, but I immigrated to the US in 2000. And I do have those 2 undergrad degrees, and right now I'm in a 2-year program in robotics. So, and again, like Sarah said, I love to hike and backpack. So this photo on the left here is me in Yosemite National Park on Cloud's Rest, and that's actually Half Dome in the background there. So that's a great time. But today I'll be talking about kind of 3 key experiences that have kind of put me where I am today. So the first one is my experience on Michigan Mars Rover, which is a student-run robotics team. And we build this robot here for a competition out in Utah. And then I'll be talking a bit about my time at NASA Jet Propulsion Lab, working on the Perseverance Rover, the Mars Perseverance Rover, which just landed a few weeks ago on Mars. Very exciting. And then also my current work as a grad student and a researcher in Michigan Robotics. Great. So some goals here is I want to highlight some cool technical things from these 3 experiences. But I also want to share kind of what's out there in space engineering and robotics, if that's of interest to any of you. And also share takeaways and tips for academic success that I've picked up through these experiences that I think could be helpful to you. So right, let's get started with MRover here. So this is a photo of the 2019 rover that we built in the competition site out near Hanksville, Utah. So this is in the desert in southern Utah. It's beautiful, and it actually does look a lot like Mars. So MRover is like I said, a student-run robotics team, and we compete in the University Rover Challenge. We've been competing since 2009. The competition essentially is made up of tasks involving like rough terrain traversal, fine manipulation using a robotic arm, which you can see in this photo here. So this is our robotic arm interacting with part of the competition. Sampling and analysis, which is really important for spacecraft and rovers on Mars. So on the right here, this is a photo of our sampling system with this little drill here that collects soil samples. Then we have instrumentation on top of the rover to analyze it. As well as autonomous navigation and traversal for the rover. So I joined MRover in 2016. So when I joined, there were about 20 people on the team, and we had a budget of about $15,000. And that competition year, so 2017, we placed 27th out of 36 in the competition field. And I was one of the sub-team leads. So that was really exciting, but next year we came back even stronger. So we recruited more people and got up to 40 people, recruited more money. And at this point, I was chief engineer of the team, which is the kind of highest technical level on the team position. And we scored in the top 10 for the first time ever, so 9th out of 36. And we kind of tried to keep this trend up. So URC 2019, more people, 75 people, almost double again, more money. And we scored 7th out of 36. URC 2020 was canceled due to COVID, but then we got a new rover ready for URC 21, and we're really hoping for podium. So, these 2 years passed, I was a senior advising mentor, but now I no longer hold a title. I let the current leadership kind of forge their own path. So I'm just an old guy on the team, but I help out where I can. So yeah, MRover was like a really, really key experience to my undergrad, and I learned a lot from it. I'm going to share just a little bit about one of the technical challenges, which is the mobility system. So during the competition, our rover has to cross about 1 kilometer of rough terrain in less than 30 minutes. And it has to do that multiple times. So this is a picture of what's called the rock garden. So we've got these like basketball-sized rocks. Also in other places, there are shrubs and drops. The operator of the rover can't always choose the smoothest path. You know, they may not be able to see all the obstacles through kind of the limited camera feeds because they are remotely operating this without line of sight. And also there's a severe mass constraint. We only have 50 kilograms for the whole rover, and we try to spend less than 20 of that for our mobility system. So my first year on the team, we thought, you know, why not make something like a real Mars rover? So we went with the rocker bogie design. So when I'm talking about rocker bogies, I'm talking about these kind of pivoted elements here on both sides of the rover. And so this looks a lot like what's on all the Mars rovers. This is the Curiosity rover, or Mars Science Lab. And you can see with this design there, these passive pivots that these members can rotate around to maintain constant contact with the ground on all the wheels. So pretty cool. That's really effective for the Mars rover. So let me pause this and go to the next slide. I never set up the videos right. Let's go. There we go. So, you know, this was good in that we have this constant ground contact, and we have even distribution of power to the ground. So we have these 6 points of contact where we can apply power to the ground. And there's redundancy, like we can afford to have a wheel fail, and we'll still have 5 left, or we can even afford to have 2 wheels fail and have 4 left and still move the rover around. But from that video, you might have noticed that Curiosity moves really slow. So the rocker bogie design is not built for speed. Yeah, so that we were lacking in. And our design is also too stiff, right? So these are all rigid members on the suspension design. And so, you know, when you're driving, if you face an impact, all of that load and the shock is going to get transmitted up into the chassis of the rover, where we have electronics and instrumentation that, you know, ideally we would isolate from those loads so that they don't get damaged. Okay, so we came back the next year and said we need something faster and we need shock absorption. Right, so we went to a 4-wheel design, and that mass that we saved from cutting out 2 of the wheels, we used on implementing a non-rigid suspension on each of the wheels. And I'll show that in closer detail here. These are rockers rather than just rocker bogies, so we still have a passive pivot that the 2 sides can rotate around. That'll become clear in the video here. If you watch this rover going over this grass, you can see that, you know, these elements are rotating relative to the chassis, keeping constant ground contact. That's me. Keeping constant ground contact. Right. And then we also have these corner assemblies. Okay, so that's a custom linkage suspension, and we also did custom spring dampers. So here's a close-up. Here's the suspension linkage that I was mentioning. This is pretty similar to what you'll see on like the front wheels of your car, actually. And we get about 3 inches of travel. We have this custom shock in there. So that's a spring and a damper with about 2 inches of throw. And then we've got hub motors. So the motors that are driving the wheel are actually inside of the wheel, and a bearing assembly, and these custom wheels for our mobility system here. So most people would buy off-the-shelf shocks. We decided we wanted to try to make our own because it was tough to find one that was in the right kind of functional range we wanted. So we've got a coil spring on the outside. Then inside here, this chamber, if you remember back to like your physics class or your fluids class, you'll know that you know, viscous forces are approximately, like drag forces are approximately equivalent or proportional to velocity, or velocity squared. So you can get viscous damping with a device like this that pushes a piston through fluid and forces fluid to flow through little orifices. Okay. So this was a fun experiment to try to build these on our own. Here is the first one we built and assembled with with kind of the structure of this corner assembly. And again, this is all student built, so this is a fun time. We also made these custom hubs for the wheels, and we pressed these in-house. So we made this die with a positive and a negative part, and we put in a flat piece of metal and then press it to make these bends for the spokes. So it starts out flat. You can see these flat spokes here. And we press it down with a hydraulic press with about 2 tons, so like about 4,000 pounds, to form it into this shape. Okay, then here's that whole corner assembly together. Got this wheel, motor installed, hub, and our linkage here. Okay, so this actually went pretty well. So we went from 27th place to 9th place with this design. The shock absorption was significantly better than before, and we could run the rover much faster. So that video I showed a few slides ago, that rover could really cruise. That wasn't even top speed. However, these dampers that we tried to make custom didn't seal. So we ended up just running them stuffed with foam instead, which achieved a similar function of like dissipating energy. But lesson learned with that, right? So there's a reason most people don't make their own. But also the bigger issue is that the suspension wasn't really oriented well for vertical loads. Sorry, it was oriented well for vertical loads, but not for horizontal loads. So in this diagram here, like a vertical load is coming up at the wheel, like as if you were to just drop the rover. It's useful to survive that, but that's not that common. Really when you're driving forward, you have these horizontal loads coming at the wheel. And the suspension system doesn't have compliance in that direction. So really this whole thing would end up getting shaped over. Okay, so then we came back with another evolution. URC 2019, so this is the same rover that I showed in the first photo at the beginning of the section. We reoriented our suspension such that it moves in this diagonal direction. And we have a component of this direction that can handle horizontal forces. Okay. So again, we got even better performance with this. This was a good incremental update. We won 7th place with this rover. But now we're facing some rising complexity. We've got quite a bit of quite a few structural members here. These linkages to transfer force up to these off-the-shelf shocks. So we stopped making our own. We bought our own mountain bike shocks. Okay. We tried another iteration for URC 2020, but this time we did something in addition to that, which was make these 3D printed wheels out of TPU or thermopolyurethane. So that's kind of like a rubbery plastic that you can print and make these wheels. And so that was cool. We didn't get to run this rover at competition, but I think it would have done really well. We also used brushless motors instead of brushed motors, so we get more power. Okay, but we're still having this rising complexity. And we want to avoid rising complexity, right? Because you're introducing more points of failure and just, yeah, more points where things can go wrong and difficulty with design. So that brings us to this year, URC 2021. We come full circle back to the rocker boat. Okay, so this might seem like a bad decision. Like, we went through this whole process of seeing what went wrong and kind of making changes according to that. Why are we doing the same thing? Well, it is actually kind of different. So now we've got this new technology, this 3D printed wheel that we can make that is compliant. So this kind of replaces the function of the shock, and the wheel handles all of that compliance we need for shock absorption. But we've reduced the part count. Even though there are more wheels on this, this is actually this has less part count, so less complexity. And we have 6 wheels, so we can apply more power to the ground and move even faster, which we decided was becoming more of a priority. So this was kind of a fun process, and like going through the years, like iterating on a design. This is just one system of like quite a few on the rover. We've got this robotic arm, which has changed a lot, as well as the electrical system and the sampling system. But we don't have time to go through all of that today. MRover, like I said, was an extremely important part of my undergrad career. And so I really want to kind of stress the importance of doing extracurricular projects for those of you, currently in undergrad. So your classes are kind of important landmark islands of knowledge. Like, they're really important, and your professors try really hard to connect them to each other. But teaching is hard. It's tough to do that. Extracurricular work, this project work, is really where you can build connections between these islands, because real world problems, don't really look like homework questions, which is a good thing and a bad thing. I'm sure you've heard that before. But extracurricular projects, facing open-ended problems, do look more like real world problems. Okay, so things you can learn from doing extracurricular projects. You can learn how to approach and break down a problem. Right, so on MRover, it's not like we have classes on how to build rovers. It's an open-ended problem that we had to break down into chunks that we could approach using knowledge from classes. But then we also have to practice independent learning. So independent learning doesn't mean solo learning. Independent learning just means, outside of classroom. You can still go and talk to experts to learn and whatnot. And then you also have to teach those things you learn to your peers. Teaching experience is great. And then you also learn leadership and teamwork skills. So with this kind of problem, you have to consider you have to think about how you can consider other perspectives when there's not necessarily a right answer, and also how to make a decision without having all the necessary information. So for that mobility system, you may learn in your dynamics class certain ways to analyze mechanisms like that. But the competition environment is really diverse, and we don't have data on everything. We can't really do a detailed analysis on every situation. And so sometimes you really just have to use your gut. Actually, quite often you have to use your gut, and then test it and see what happens. Okay, and then you also have to learn how to work with people outside of your discipline. So that can be other types of engineers and scientists, but also business people, artists, or educators, and many other types of people. And that's a useful skill. So you might be asking yourself, what if I don't have a project team I want to join? So there are a few options. So one, you can start one. That's a really ambitious goal, but it's a great thing to do and a very impressive thing to do. You can start a URC team and compete with us with MRover. But there are also tons of other collegiate engineering competitions. You are allowed to ask your school and local businesses for sponsorship, so you don't need to fund this on your own or anything. So that's a great option, but you also don't have to start a competition team. You can just get a group of friends together or your peers to make something for fun, or to make like a tech club. So I'd recommend, kind of, if you're taking on a personal project or a project with a small group, check out this website, hackaday.io. I'm sure some of you already browsed this, but on Hackaday and on YouTube, people are posting like tons of these projects that they do. You can use those for inspiration. You can start, by recreating those, but also improve upon them. And that's a great way to learn practical skills and some of the skills I was talking about on the previous slide. And you can also ask for funding for this. And then finally, you can also pursue research as an undergrad. So research is not just for grad students. And that's a good option if you're considering grad school, which I will get to kind of in the third section of this. And then finally, if you get enough engineering from your classes and you're sick of engineering day to day, totally reasonable. You can also get involved with something that's not technical. So any pursuit that you can immerse yourself into and become passionate about is impressive on your resume, and it's a worthy use of time. So if you're interested in more about MRover, we have this website. Let me let that little thing go away. Okay, mrover.org. Cool. So now I'm going to move on to my time at NASA Jet Propulsion Lab. So right here, this is a photo of a very close copy of the Mars Curiosity rover, which landed on Mars back in 2012. And so this copy exists here on Earth because oftentimes, while operating the Curiosity rover on Mars, operators might encounter a situation that they're not sure is safe for the rover. Like, can I climb over this rock or something like that? What they do is they actually take out this rover and try to find a similar rock. Sometimes they'll even sculpt a rock to like look like that, put it on the ground and see if this rover can do it. You know, if it can, then they feel more confident in executing that operation on the real Mars rover. So this is pretty cool. You can just kind of walk up to this rover on lab at JPL. So an overview, NASA Jet Propulsion Lab is one of 10 major NASA centers. And it actually predates NASA by a few years because it's also part of California Institute of Technology. So it started out at Caltech. But now it's got about 6,000 employees, which is much bigger than Caltech itself. And it's responsible for all successful Mars rover missions and also many, many other projects from other planets to also on Earth. Okay, so I spent a co-op there from January to August of 2017. So co-op is just an internship where you take school off and you work longer. So I took that spring semester off. And then also I returned for an internship May through August of 2018. So I spent just under a year there cumulatively. And I learned a lot of stuff. So I was working on Mars rovers. This is kind of a quick history. So the first Mars rover that JPL put on Mars is this little guy, the Sojourner rover. This was part of the Pathfinder mission. So this rover actually rolled out of a lander. Okay, and it's quite small compared to the next one up, which is the Mars Exploration Rover. So this is like about like a small golf cart size. Or MER. So there were two of these rovers, Spirit and Opportunity. Spirit ended its mission a few years after landing, but then Opportunity actually kept going for about 14 years after landing, so 2004 to 2018. So unfortunately, it's no longer operating, but it lived a good long life. And then kind of another upgraded size here is the Mars Science Lab, or Curiosity rover. So this is about the size of a Mini Cooper, and it's about 1,000 kilograms, so quite big. Okay, and then now to today, we've got the Mars 2020 rover, or the Perseverance rover, which is very similar to the Curiosity rover, but carries more sophisticated instruments, and we think is going to be a little more reliable. If you're looking for an easy way to spot the difference, first thing I'd tell you to look at is the wheels. So the Curiosity rover has these wheels with these sharp corners on these browsers. The lines on these treads are called browsers. But Perseverance actually has wavier ones, which are stronger. So Curiosity is in a bit of trouble because its wheels are breaking apart. These sharp corners give rise to stress concentrations, but these new wheels are stronger. Great. So on the top of the rover is this structure here. So this tower with the swiveling camera on top, as well as a bunch of other instruments. This is called the remote sensing mast. So when I was there, I was on the remote sensing mast mechanical team. So this is me next to our engineering unit, which is basically identical to the flight unit, along with the gold-plated camera on top. And I'll explain what that's about in a second. And I'll also explain why I have to wear this funny suit and work in a clean room. So I was one of 6. We had a team of 6, so there were 4 engineers and then a technician, QA person on this RSM team, on the mechanical team. So my role was mechanical design, structural analysis, so think like FEA, finite element analysis, and also integration and test. So integration is just assembly, and that's what you need to do for flight hardware. There are a lot of kind of jargony terms in the industry, but I'll explain them as I go. Cool. So, you know, kind of a stark contrast from the previous section. This is MRover's collegiate rover, built with about 75 people for about $25,000, and we spend a year building this. But the Perseverance rover, right, involves approximately 1,000 people, across not just JPL, but also many institutions that contribute and companies. $2 billion, and it took 10 years to build this. Actually, a little more than that, really. Okay, so other than gold-plated cameras, what makes this so much harder to do? Like, this is a massive increase in scope compared to this, what we do in college. So let me talk about a few cool technical stuff that might shine a light on that. So first, back to that camera, that is SuperCam. So this is one of several science instruments on the rover. So what it does is, so it's got a lens cap on right here, but behind it, there's a lens. Out of the center of that, it fires a laser at samples up to 7 meters away, which creates a tiny puff of vapor coming from that sample. And then it uses optical spectroscopy to read the composition of that puff. So that's called laser-induced breakdown spectroscopy. It's a really powerful tool to understand samples without having to touch them, hence the term remote sensing. Okay, you can also do 3 other types of spectroscopy: Raman, time-resolved fluorescence, and visible IR. So some of you physicists or geologists in the crowd might recognize these instruments. It can also produce high-res color images. Right, so on the right here, this is the first time we tested the engineering unit. So there's, for most things, there's 2 copies. There's an engineering unit and a flight unit. We use the engineering one on a day-to-day basis to keep the flight one, safe and intact. So this is the first time we put it on the RSM structure, and it is gold-plated for thermal reasons, which I was not involved in, so I can't really explain too much more about that. Like I said earlier, a lot of people from different institutions contribute to the rover. So SuperCam is actually a collaboration between JPL, Los Alamos, IRAP in France, French Space Agency, University of Hawaii, and University of Valladolid in Spain. Cool. So another cool piece of tech here, this is the Ingenuity helicopter, which you may have heard of by now. So this is the first, if it works, it'll be the first powered flight on Mars. But it's a technology demonstrator, a tech demo. So these are missions that are, not primarily focused on science, but rather are explorations to see if we can pull something off. So if we can actually fly on Mars. Flying on Mars is a huge challenge because Mars has, lower gravity, which is good because that, that means that it's easier to get off the ground. But it only has 1% of Earth's atmospheric density. Okay, so that makes flight really difficult. If you think about us, taking a swim, right? We float in water because water is dense, so we can swim in it. But we don't float in air, right? So we can't swim through air. So this is kind of analogous to that. So helicopters work well in the thick air on Earth, but the thin air on Mars, that's a whole different challenge. Okay, so this lower picture here is actually from a day or 2 ago. The rover dropped this dust cover, revealing the helicopter on the bottom of the rover. So it's going to get ready to put it on the ground soon for a flight, which is really exciting. It might make a flight in the next 2 to 3 weeks. Okay, one more cool piece of tech. So some of these things that I'm talking about, you may have heard of, or you may not have. One of my goals was to kind of talk about things that may not get the mainstream coverage. One of these things is the bridal umbilical device. So this is a mission critical mechanism. It's used to lower the rover to the ground. Okay, so during the entry, descent, and landing, which is when the rover gets to Mars, it's coming in as this like spacecraft pod. Okay, and it slows itself down with the parachutes, but really the hairy part of it is the sky crane maneuver, where we have this rocket-powered jetpack, which is how I've heard it described. I think that's the best way to describe it. Called the sky crane, that actually lowers the rover down on these bridles or ropes. Okay. So this is a photo from a few weeks ago of what that operation actually looked like. So this is a real photo, which is amazing. What's actually lowering the rover to the ground, though, is just this spool of bridles attached to a brake. And what's particularly cool about this, in my opinion, is that this mechanism is totally passive. So you might think that there should be some motor in here to like precisely lower the rover down. That's not the case because that's a point of failure. Putting a motor in space is really hard, and they try to minimize how many are in space. Instead, it's an electromagnetic brake, again, that provides damping force similar to that spring damper I was talking about earlier. So it'll provide a torque that's proportional to the velocity of this, angular velocity of this drum. Okay. And once this completely unwinds, the rover's on the ground, the attachment points on the rover, the bridles are cut there using explosive guillotines. So these are blades. There's blades in an assembly kind of going around the rope that get jammed into the rope by an explosive charge. And these are used because they are 100% reliable in space. So, well, according to my boss anyway, none of these have ever failed in space, which I think is really cool. Yeah. So this is the actual video from the touchdown. It's amazing that we have this video. So the same kind of sequence was done for Mars Curiosity, but we didn't have the capability, or we didn't have video of it, but now we do. So I'm just gonna let this play. And again, I think this is amazing. Many of you may have already seen this. So we've got this parachute deployment. Okay, then this shot is really cool. That's the heat shield coming off the bottom of the spacecraft. So that heat shield is there through most of the descent through the atmosphere, because there's a lot of heat generated from flying through the atmosphere. But then once you get low enough, you don't need it anymore. And this is now the rover has a view of the ground, so it can conduct scans and figure out where to land autonomously. So I'm going to up the speed here. I don't know if you all think this is as cool as I do, but that's actually Mars. I think that's crazy. It's going to sail down. So during this whole process, Mars is pretty far away, so there's a delay in communication due to the speed of light, to the tune of about 7 minutes. So it's 14 minutes there and back. This whole process happens faster than that. So this has to happen completely autonomously without human intervention. So by the time we know what happens, it's already happened. See, let me change the playback speed back to normal here. Okay, so this is dust flying around from those jets on from the rocket engines on the sky crane, and then there's those bridles lowering the rover down gently. Okay, so then the wheels deploy. Makes the cut, and then that flies away. So really cool. It went off as smoothly as it possibly could. So I thought I was really happy to see that. Okay, so what makes this so hard, right? Think about the conditions that we face when we're engineering stuff for space. So thermal conditions, right? So when you're building stuff on Earth, your spacecraft has to function on Earth to test it. It's 20 degrees Celsius. In space, it's way colder. It's negative 200 Celsius. It's actually technically colder in space, but it's a little warmer next to the spacecraft. Then on Mars, it's negative 100 degrees Celsius. Right? So that's a 220 degree Celsius range of temperatures that this thing has to work in. Very few things on Earth have to have that kind of requirement. So similarly, on Earth, we've got a full atmosphere of pressure. Then in space, it's a vacuum. And then on Mars, it's a really, really thin atmosphere, 6% of an atmosphere. Okay. You have no magnetic field protection on Mars, so radiation can hit the rover. which is really tough on electronics. During the actual launch, we have high accelerations and vibrations. And also during that entry, descent, landing sequence, you have high accelerations and tons of dust flying around. Right? And this whole thing, you have to make something that can withstand that with the limited mass allowance. Okay, and there are tons of other factors. So space engineering is like this crazy challenge. Right? So I'm going to highlight a few challenges. Okay, so first one, planetary protection, which sounds like a cool sci-fi term, like maybe the Space Force. But that's actually not what it is. For spacecraft, planetary protection is the concept of keeping organic Earth stuff off of Mars, so avoiding biological contamination. You need to do that because otherwise you won't be sure if you find life, if you just brought it there with you. Okay, so everything needs to be extremely clean. Everything gets baked out in a vacuum. So you put it in an oven that's also a vacuum chamber to kill everything on it. And then working with it, you have to wear these bunny suits, which are what these folks are wearing here in a big clean room. Okay, and then whenever you're bolting stuff together and there's like a sealed interface, you need to make sure that's clean. So before you seal it up, you actually swab it and people test it for contamination. If it comes back that there was contamination, you have to open it up, clean it up, and redo it. And then, it goes down to every detail. So every single screw, we have to ultrasonically clean it in acetone and then alcohol, and then wipe it by hand with a lint-free sterile cloth, and then store it in a sealed anti-static bag. So all of this might seem overkill, but it really comes down to the details. So JPL is the only organization that's been able to successfully put something on Mars. And so this is the JPL way, right? This is the way, as Mando would say, bringing Star Wars fans here. Cool, so then another challenge is that you're limited on materials you can use. So most materials we use on a day-to-day basis are not suitable for space because they outgas in a vacuum. So what that means is that they degrade and give off vapors in a vacuum due to that low pressure. And that actually, ruins the materials and can cause contamination on your sensitive scientific instruments. Right? So you need to use vacuum-safe materials like specially coated aluminum, titanium, stainless steel, Inconel. If you need plastic, a popular one is Ultem polyethylamide. So this is like a really expensive plastic that's vacuum safe. If you need tape, you need to use Kapton tape. So it's basically like space duct tape. All of this orange stuff you see on this assembly here, that's all Kapton. We use like a lot of it. You need special lubricants, special electrical isolation for insulation, for like all of the wires on the rover. And you even need special paint. So this is a part fresh from the paint house with a really special vacuum safe paint. This stuff is super fragile and it chips really easily. So assembling stuff after it was painted was a real pain in the butt to make sure you don't ruin the paint. Cool. And so all of this you have to keep in mind. Everything needs to be reliable. Like everything has to work, right? So taxpayers are spending $2 billion on this. People are spending, their careers on this. It's really high stakes. So all of the electronics are radiation hardened. Consumer electronics don't survive in a radiation atmosphere. They start creating errors very fast. There's also redundant onboard computers. So there's like a main computer and then there's an exact copy on the rover. So you can have your main one completely fail and have another one good to go. Everything is tested. So GSE, short for ground support equipment. I meant to define that before, but that's basically anything you need to build to help you build the spacecraft. So all of that needs to be tested before it's allowed to touch flight hardware, to the tune of like 5 times the load. So if you need a fixture to mount, a 10 kilogram assembly and work with it, you need to test that fixture to like 50 kilograms to make sure that there's no risk of it breaking or damaging the flight hardware. Okay, so then everything needs to be tested at all the relevant temperatures and pressures, which is a huge range. And then any operation involving flight hardware including the simplest stuff, just like screwing connectors on or like putting a tiny piece on with 2 screws, must have a written procedure checked by quality assurance. So anytime we go into the clean room to put together flight hardware, we'd come in with pages and pages of these procedures written and checked. So basically, mistakes are not allowed. Okay, so that sounds scary, but the system's actually designed to remove that pressure from any one individual. So it's not like I was coming into work every day with the entire weight of the mission on my shoulders. I made mistakes, my coworkers made mistakes, my boss made mistakes, but the system is designed that all of those are checked and caught and fixed before anything can go wrong. And that's totally normal, and it's great because you have an opportunity to learn from those mistakes. So pretty cool. It's a really deliberate, detail-oriented process. Great. So some takeaways from this experience. As you might have guessed, I picked up a lot of attention to detail, and that served me well ever since. Also, I've learned, it's really just easier to do things right the first time. Do it slower, measure twice, and cut once, as they say. And of course, lots of technical skills, mechanical design, analysis, drafting, tons of stuff, but also teamwork skills. Okay, so I'm guessing quite a few of you are listening to this talk because you might want to work at NASA, but also, anywhere else you want to work, I have some tips for you. So first thing, pursue a co-op. So that means you need to take a semester off to intern. Typically, co-ops have a less competitive applicant pool because fewer people want to do co-ops because it delays your graduation. Delaying your graduation doesn't really matter. Don't worry about that unless maybe you have like a scholarship or something, but try to work it out with them. Try to pursue a co-op. You can gain more experience and you're facing less competition. So that's good. Get practical experience. So like I was talking about in the previous section, project teams are great. Research is great. Personal projects are great. Interviewers look for practical skills. Okay, and then finally, or not finally rather, but cold call and email people in the organizations you're interested in working for. So find out names and contacts through LinkedIn or like press releases or anything else. Do your research, prepare meaningful questions, let them know you're interested in working. You might not get a lot of responses, but it's a numbers game. Just send them out, dozens at a time. It's really important. It feels futile, and then one comes through and you have a contact, and it's great. Okay. So then also, when you're reaching out to these people, it's really helpful to have a portfolio or a website to show off your work. If you don't have project experience yet, like it's okay to show off your classwork, if you have lab classwork and stuff. But a portfolio or a website is way easier for recruiters to look at than another resume because they look at hundreds of resumes every day. Okay, so if you have an interview coming up, maybe it's with JPL, maybe it's with another organization you're really interested in. So obviously, read up on the interviewer and the organization. What projects do they work on? What makes them unique? What are they uniquely capable of? What challenges have they addressed? Okay, so do your research, keep all of that, make detailed notes. And then when it's time for the interview, remember that your interviewer is really just a normal person. Before you know it, after college, you're going to be interviewing people as well. I've had to interview people, not for jobs, but for other things. And yeah, your interviewer was once in your own shoes. So don't worry. Okay, so they don't expect you to already know everything. Because you don't learn all the specific things you need to know to function in a job. You learn that on the job. So they're looking for your ability to learn outside of a classroom environment. So again, project team experience, personal projects. Okay. So they're also looking for someone they could spend 8 hours a day with. So just act natural. Try to empathize with them on this. So think like maybe you're starting a new class and you want to put together a study group. Like who do you want in your study group, right? It's not necessarily just the person who gets the highest grades and is the absolute smartest. There's more to it than that on how well you can work with them. So consider that. Okay, and then lastly, if you're in an interview, that means they have an open position, and that interviewer would like to fill that position as soon as possible because they don't want to be doing interviews months on end. They have other work to do. So really, they're looking for an excuse to hire you. Okay, so just give them that excuse, go in confidently, and you will be fine. Okay. So even if you don't have an interview coming up, try to make connections anyway. Again, via LinkedIn or other contacts, maybe through your professors or other people you meet. And ask them for advice, or take a look at your portfolio or resume. People really like giving advice, like I'm doing to you right now. So if you ask them for advice, you're more likely to get a response. Cool. Okay, so then if you go through all of that and you don't get your dream job on the first try, don't panic, don't fret. Reflect on your interview or the recruitment process and take detailed notes. Ask for feedback from your interviewer. Sometimes they won't give it. That's okay, but it never hurts to ask. And then pursue roles at places associated with where you're originally trying for. So if you're really interested in JPL or working on a Mars rover, it's not just JPL. All of these other organizations also contribute to that rover. And this is just a few that kind of I picked out from the top of my head. So tons of universities, these other companies, all contribute to that rover. And so do your research, find out these companies and apply to those too. Let me take a drink of water real quick. Sorry, I'm going fast. I have a lot of ground to cover. If you want to learn more about the rover, they have this cool website where you can play around with this 3D model. I'll let you click on that later if you want. But now to talk about a little bit about grad school. And I'm gonna go fast here so we have time for questions. These are some photos of hardware that I'm working on with my research. I can't really actually share that much technical stuff because we're not published yet. And we're kind of keeping it close to the chest, but eventually it'll be open source. All right, so I'm doing my master's in robotics at University of Michigan. So it's a 2-year program. Part of that program is doing at least a semester of research. So I'm in that semester now and I'm continuing it into the summer with Dr. Talia Moore. Talia is a biologist and this is what the lab is about. I'm just gonna read out these bulleted sentences here. So 1, we design bio-inspired robots for animal-robot interaction experiments and to test evolutionary and ecological hypotheses. Okay, but then there's a flip side of that coin. We also build tools to improve robot performance in complex environments by examining animal motion in the real world. Right. So what I'm working on is legged robots. These are some popular ones on the scene right now. You might recognize a few like Boston Dynamics, Spot Mini, but there are quite a few more than just Boston Dynamics. These are all like really, really impressive pieces of engineering, but they don't actually really look like animals. So animals have more joints than these. And they're also not built for use by biologists. Right? So this is kind of where our take comes in. Okay. So we want to make a robot that's useful to biologists and a robot that can behave more like animals. Let me show you this video of MIT Mini Cheetah. This is, again, a really impressive robot. And it does look pretty lifelike, right? Like it's got some character to it. It can walk sideways. It can walk in circles. It's pretty capable. It can actually also do backflips. I didn't show that because animals don't really do backflips. But pretty cool, right? Okay, that still doesn't really come close though to what animals can do. So this is a clip springer playing with the dog. And kind of watch how it can seamlessly change its pattern of motion, or what we call a gait, across different substrates. So it's on dirt, it's on concrete. It can just hop around really spontaneously. That's really hard for a robot to do. Basically, no robot is capable of this kind of like seamless and diverse locomotion right now. See, that hop was really impressive, right? These hops in place, also impressive. They're also really cute. Okay, so we want to kind of push this envelope a little further and make robots that can, approach something like that. There we go. Okay, and then another animal I'd like to show you. So this is a jerboa. My PI Italia spends a lot of time studying jerboas. They're really cool. So again, we want to make a robot useful to biologists and one that can behave like animals. I can't really share with you kind of what our approach is because, again, we're submitting a paper in the fall. After that, then I can share it. But I just wanted to give you a taste and also have an excuse to talk about grad school. I didn't really know what grad school was until it was time to apply. But I think the key thing here is those of you who are upperclassmen, think about how much more you learned in senior year than in junior year, and in junior year than sophomore year. So it's kind of like an exponential trend for how much you can learn in a year. And that continues into grad school. So grad school is a great time to harness all of that momentum and learn even more. There are patterns in your work that may have only just become apparent to you as an upperclassman. Grad school, you can spend more time with those and really kind of gain mastery of it. Okay, and also if you get a master's, you'll get a higher salary, about 8 to 15% higher for most technical roles. So, sorry, I kind of rushed through that. If you're thinking of grad school, start looking for schools and professors, reach out to their students and ask them what the lab is like. Read papers while you have access to journals and publication outlets in college. This is really tough to do. Maybe get a study buddy or a group of people to read papers together and try to figure out, what that paper is saying. And you can also get involved in research as an undergrad. That's a big plus on your application. And start your applications early. So that was pretty much all I had. Sorry, I went a little longer than I want, but we do have some time for questions. So please feel free to ask me anything.
Thank you, Karthik. That was really interesting.
Thank you.
Yeah, we have a few minutes for questions. So especially our undergraduates here today, if you would like to ask a question directly or put something in the chat, now is your chance. Professors?
Until we get a question, Karthik, thank you so much for being here. And there are so many people who wants to be here, but either teaching a class or in a class right now. And I got so many emails and text messages saying that, are you recording this? Because I really want to, listen to you. So this will be shared. The recording will be shared among many. I just wanted to let you know that. So thank you. It's very interesting.
Yeah.
Oh, we have a question in the chat. How does one get an explosion to occur in a vacuum?
That's a really good question, actually. So for combustion, you need oxygen, right? Or you need an oxidizer. So you can make that happen in space by including an oxidizer with it, instead of just relying on oxygen from the atmosphere. Right. So those explosive charges have the fuel and the oxidizer. And I don't know too many more details than that, to be honest, but that's the gist of it.
I have a question. I was wondering what when you finish your master's, kind of what are you envisioning next for yourself?
That's a good question too. I'm considering a PhD, considering the research I'm currently working on. I'm also considering going back to JPL, to NASA, or there are also other kind of organizations in industry that are interesting to me that I'll be applying to. So we'll see. That's more of a next year problem. So
okay,
yeah,
fair enough. Let's see. Jaden has a question.
Yeah. Can you hear me?
Yeah.
Yeah.
Yeah, so I just did a presentation in one of my classes regarding using active suspension and semi-active suspensions. If you're familiar with that at all, do you know if there are any limitations to applying that to using sensors and stuff like that to take feedback from the environment to anticipate and adjust your suspensions for spacecraft and things like that?
That's a great question. People are definitely interested in this. Okay, so when spacecraft technology is actually pretty far behind like Earth technology, because you can only send stuff to space to Mars really if you know it works, right? So all the stuff on the Mars rover is tried and true. So active suspension isn't there yet, but there are people kind of working on these R&D projects. And so, these rovers have tons of perception equipment on them to the point where they can like 3D model the terrain. And I could envision that knowledge being used to kind of optimize suspension for traversal. Now, I haven't like read any papers on that or anything, but yeah, we may see that in the future.
Thank you. That'd be really cool to see happen here soon.
Absolutely, yeah.
I do have another question, Karthik. So I think you mentioned that, although the mistakes are not allowed, it's been taken care of already with all the, the system, right?
Mhm.
But is it like stressful working at NASA, or like, would you want to go back and, be a maybe like full-time, position there at NASA someday? If that's offered, would you be willing to take that, apart from all the stress? And I don't know whether it's stressful, but looks like you have to like pay attention to details, and the work is like tedious. What do you think?
It's okay, so it is tedious, but it's not stressful. I mean, I guess it's stressful for like the higher level people, they have more of a stake in it. But like, for the kind of lower level engineers and interns, I wouldn't say it's stressful at all. It's, you have to do a lot of learning and a lot of thinking. And if you make a mistake, it's not like you get, yelled at about it. It's not a penalizing thing. It's a learning opportunity. It's I don't think you can find JPL has 6,000 people. I don't think you can find a population of 6,000 people who don't make mistakes. So really, it's kind of encouraged to think through these and learn from them, because that's better than trying to just recruit people who don't make mistakes. That's impossible. I would consider going back to JPL. So I didn't go back because flight projects are like pretty slow. So this rover took 10 years to make, for good reason. But kind of there's interesting robotic challenges here on Earth with a faster development cycle. So I'm kind of interested in exploring this first.
Thank you.
Any other questions? Oh, thank you, Karthik, for being here today. Sounds like you've had a really interesting career so far. I'm sure you're going to have lots more cool stuff coming up ahead. So thanks for sharing with our students. And I'll send you a link for the recording.
Great. Okay. Thank you. Thank you all for coming, and thank you all for the good questions. And yeah, good luck with your schooling and your research or whatever you're working on. And maybe I'll see you all later.
Great. Have a good day. Thank you.
Bye.
Thanks. That was a good talk. I really wanted to go into details about these